Hey everyone, welcome back to the channel. Today we're diving into the brain behind some of the most powerful language models out there. Think ChatGPT, Gemini, Claude, and even models like Llama and DeepSeek. We're talking about the transformer architecture. It all starts with inputs prompt. This is the text you feed into the model, maybe a question you ask ChatGPT, or a sentence you want translated. The first thing the transformer does is turn these words into numbers. This is called input embedding. Essentially, each word gets its own unique numerical representation that captures its meaning and relationship to other words. Think of it like giving each word a special secret code. But just knowing the meaning of words isn't enough. The order of words in a sentence is crucial. That's where positional encoding comes in. It adds another set of numbers to the word embeddings, telling the model the position of each word in the sequence. So, the cat sat is different from sat the cat, and positional encoding helps the model understand this difference. Now these combined word meanings and positions go into the encoder. Think of the encoder as the part of the transformer that understands the input text. It's like the reading comprehension expert. Inside the encoder, one of the most important parts is multi-head attention. This is where the magic really starts to happen. Imagine the model looking at each word in the input and asking, hey, which other words in this sentence are most important and related to me? Multi-head attention does this multiple times in parallel. That's the multi-head part, allowing the model to capture different kinds of relationships between words. For example, in the sentence, the cat chased the mouse, attention would help the model see the connection between cat and chased, and mouse. After the attention mechanism, we have an add and normalize step. This is a common technique in neural networks. Add refers to adding the original input from before the attention back to the output of the attention layer. This helps the model retain important information. Normalize helps to stabilize the learning process. Next up is the feed-forward network. This is another layer that processes the information from the attention mechanism further, helping the model learn more complex patterns in the data. We have another add and normalize step after the feed-forward layer, again for the same reasons. Retaining information, stabilizing learning. This whole process, multi-head attention, add and normalize, and feed forward, can be repeated multiple times within the encoder. Each repetition allows the model to refine its understanding of the input text, building a rich representation of its meaning. Now let's move over to the decoder. This part of the transformer is responsible for generating the output text, like the answer to your question, or the translated sentence. Just like with the input, the decoder also starts with output embedding. If it's generating a sequence word by word and positional encoding to keep track of the order of the words it's producing. Notice here the outputs. Shifted right. This is a clever trick used during training, where the model is essentially shown the correct output, but shifted by one position, so it learns to predict the next word. The first key component in the decoder is masked multi-head attention. This is similar to the attention in the encoder, but with a crucial difference, the masked part. When the decoder is generated at output, it can only look back at the words it has already generated. It can't see the future words in the sequence. This prevents it from cheating during training. Again, we have an add and normalize step to help with information flow and stability. Next, we have another multi-head attention layer, but this time it's a bit different. This attention mechanism allows the decoder to look at the encoded representation of the input sequence from the encoder and the words it has already generated. This is how the decoder connects its understanding of the input to the output it's creating. It's like saying, okay, I understood the question, and so far I've generated these words. Now, what should be the next word based on both of those things? And you guessed it, another add and normalize step. Just like in the encoder, the decoder also has a feed-forward network to further process the information. And one last add and normalize, to ensure everything is smooth. Finally, the output of the decoder goes through a linear layer. This layer takes the processed information and transforms it into a score for each possible word in the model's vocabulary. The very last step is the softmax function. Softmax takes those scores and turns them into output probabilities. Essentially, it tells us how likely each word is to be the next word in the sequence. The word with the highest probability is then chosen as the output. And that, in a nutshell, is the power of the transformer architecture. It's the core technology that allows these incredible language models like